Okay, we should be live. Just check LinkedIn because it's the only one. I can't just go live with a press of a button. I have to set it up every time. Okay, where's the list of what we are covering today? Pop it in here for a sec. Did I misspell visualization? No, just suggesting. Interestingly, it's not suggesting American spelling, it's suggesting the English one with an S, but yeah, no one cares, really, I think. Let me know if you do. Well, actually, yeah, this topic. Rewind. We'll cut it in the editing. So the general overview that I always do, we are covering Bionic Chaos on this site. Well, that's quite obvious because that's what the YouTube channel is called. But these are the tools available on the site. Please go check them out. They are on bionicchaos.com. Let me know what you think. Currently, we have these tools at the bottom that are still under development. Well, they actually not under development. They used to work, but they used to be LabVIEW and MATLAB. Now we don't have access to those. The license is too expensive. So we redoing it in Python and JavaScript. Eventually making a Flask application that most of these tools are. They will be available for you to play with. So I don't know if you know much about fuzzy logic. Most people know about neural networks. Fuzzy logic could be better in the sense that it's more explainable. You actually can see what is it doing, how it's making decisions. The neural networks, well, depends on the complexity of it, not so much explainable. Now, so as you know, we mainly dealing with EEG and ECG data on this channel as part of this project. Some other image processing a little bit, and other things are welcome too. Please let me know in the comments if you wanted to look at any other data. The data for this project will have to be publicly available. So send me a link to the public repository of any data you wanted to look at. Now, yeah, so we currently trying to get the fuzzy logic example up and running again, but we thinking how to do it. Originally it was a simple example of various simple shapes detector. Those were time series waveforms, but then we thought we might as well do it a little bit more useful. So we tried applying it to synthetic EEG that has a seizure in it. We do have some real EEG data that we are working with, so we could apply it to that, maybe at a later stage. Synthetic signals are always good because you know exactly what's going on with them. And because we're working with ECG data as well, and one of the tools that we have on the side that was quite popular is this ECG game. We will use that one to develop a fuzzy logic and neural network application that will essentially play the game and do detections for you or against you. So it would be interesting, so you could see how well you are performing against the bot. So we're already doing this project. Generally, that's the comments where they no, this way. It's a mirrored image. So we're doing a waveform. So generally, we're doing waveform detection using AI, looking at the signal abnormalities and noise. We're using fuzzy logic and or neural networks. Obviously interested in data visualization. Currently for this application, we are using Flask, NumPy, SciPy, and SK Fuzzy, which is the fuzzy logic toolkit for Python. Probably know about the other ones already. If not, there's a lot of other content on YouTube that will cover those. Let's check if there are any questions quickly before we move on. We are streaming everywhere, pretty much on Twitter. There's no questions. LinkedIn, no. And YouTube, no questions. Let's move on. Just no one wants to talk. By the way, there is an option of you coming live on this stream if you like. I can set up a Zoom room that you can join in, and potentially instead of this text, your face will appear, and we can just have a chat. But if no human is up for a chat, we'll talk to the bot. Unfortunately, it is second best, but that's what we have for now. Okay, so we are live streaming right now. These are the topics that we cover in this stream. We would like to continue development that we did last time. Can you mention how many prompts are in the current conversation? And give a quick summary of the changes to the code that we made. Yep. I wanted to respond quickly and short.
Absolutely. Let's summarize the progress and topics covered in this conversation so far. Total prompts in conversation. We've interacted through a series of 16 prompts, including this one. Topics and development overview. Waveform detection using AI. We've been focusing on developing a system for ECG waveform analysis, particularly detecting abnormalities and handling signal noise. Fuzzy logic, neural nets. We discussed the implementation of fuzzy logic in your system. This involved debugging and refining the fuzzy _logic _analysis function in your Flask application to correctly process ECG data and calculate fuzzy logic outputs. Data visualization. While we haven't directly worked on visualization in this conversation, your project involves visualizing ECG waveforms and the results of the analysis, likely using tools like Flask and JavaScript for web-based interaction. Flask, NumPy, SciPy, SK-Fuzzy. Flask. We focused on the Flask backend, particularly on routes handling ECG data processing and analysis. NumPy and SciPy discussed their usage for processing ECG data, including Fourier transforms for frequency analysis and peak detection. SK-Fuzzy addressed issues in implementing fuzzy logic using scikit-fuzzy, particularly in handling membership value calculations. GPT-4 and GitHub Copilot briefly compared their uses in coding. GPT-4, ChatGPT, is ideal for explanations and understanding concepts, while GitHub Copilot excels in real-time coding assistance within an IDE. Key code changes made. Frequency calculation, suggested modifications to the frequency analysis part of your code to correctly identify the dominant frequency from ECG data. Peak count logic, advised on adjusting the peak detection logic to align with your project-specific requirements, e.g., counting positive and negative peaks. Troubleshooting fuzzy logic, offered solutions to fix issues in your fuzzy logic analysis, including correctly extracting and serializing membership values, and handling cases where fuzzy rules might not be triggered. Feel free to ask if you need more specific details or further assistance as you continue with your development during the live stream.
Yes, we actually haven't implemented the changes for the problem that frequency is always showing 0 at the moment. Sampling rate is a good question. Can you look at the waveforms JS and tell me what the sampling rate is? I'm pretty sure I'm already doing FFT frequency analysis. So what are the changes I need to make that it's to make sure it's not showing 0 all the time? Now, regards the normalizing the peak counts. So yeah, it sounds good that we have them split into positive and negative peaks. That code had the microphone failing on us because we're using the microphone in
Sure,
different
let's
places.
keep it brief and to the point. Sampling rate in waveforms. JS. To determine the sampling rate from your waveforms. JS. I need to see how the data points are generated over time. If you can show the part of the code where the time intervals are set or how the waveforms are updated, I can help deduce the sampling rate. Adjust frequency calculation. Implement the correct Fourier transform method considering your sampling rate. Use np.fft, FFT for Q to get the correct frequency values. Code change. Python copy coder sampling _rate equals. Hash define this based on your data's time intervals. Frequencies equals np.fft, FFT for Q, len, np_data, d equals 1, sampling _rate. Dominant frequency equals abs, frequencies, np.abs, np.fft.fft, np_data, argmax. Separate positive and negative peaks. Use Skippy. Signal. Find _peaks for positive peaks and the same function on the inverted data, np_data, for negative peaks. Direct use. If specific numbers of peaks are expected, e.g., 3 positive, 1 negative, compare directly with these expected values instead of normalizing. Let me know if you need more details or further clarifications.
Okay, on the peak detection. Okay, first of all, do you have access to the previous code that I already shared? I already shared the waveforms.js with you. Can you also mention, this is low priority, but how does the limit of 40 messages per 3 hours work? How can I tell what's my current message count per time window? Yep.
Yes, I do have access to the previous code you shared, including the waveforms, JS script. Let's dive into that to deduce the sampling rate. Regarding the message limit, as a language model, I don't have the capability to track or display the current count of messages or time windows. Typically, users manage this by keeping track of their usage. If you're concerned about reaching the limit, consider spacing out your queries or consolidating multiple questions into a single message where possible. Now, let's analyze the waveforms, JS script to determine the sampling rate. Could you please provide the specific section of the waveforms, JS that includes the waveform generation or time interval setup? This information is crucial for accurately deducing the sampling rate.
Okay. It's not very useful. Let's try GitHub Copilot. And then we also, reduce the load on GPT-4. Yes, it seems like you're detecting both positive and negative peaks. That's correct. You're not using those values. Now I don't want to add them together. I don't want to add them together. I want to use them separately because they are important. Okay, for the number of positive and negative peaks, considering a normal ECG waveform, how many of them there should be in a normal ECG waveform? A single QRS PQRST complex. Yep.
In a normal ECG waveform, which typically represents one heartbeat, the key components are the P wave, QRS complex, and T wave. Here's a breakdown of the peaks. P wave represents atrial depolarization. It's a small positive peak. QRS complex reflects ventricular depolarization. It usually consists of a small negative deflection, Q, a large positive deflection, R, and then another negative deflection, S. T wave indicates ventricular repolarization. It's a positive peak. So, in a typical normal ECG waveform for one cardiac cycle, a single PQRST complex, you should expect positive peaks, 2, P wave and T wave. Negative peaks, 2, Q and S waves in the QRS complex. The R wave is a larger positive peak within the QRS complex. Keep in mind that variations can exist in different individuals and under different physiological conditions, but the above describes a standard normal ECG waveform.
Well, right, so how would you suggest changing that feature processing by the fuzzy logic detector? The detector meant to give higher probability for a abnormal EEG. So it has abnormality, unlikely, possible, or likely options. Yep.
To adjust the fuzzy logic detector in your system to give a higher probability of detecting abnormal ECGs, you should focus on tweaking the fuzzy rules based on the ECG features you're analyzing, namely, frequency, amplitude, and peaks. Since we've identified the standard peak pattern in a normal ECG, 2 positive and 2 negative peaks, you can use this information to refine your rules. Here's a suggested approach. Define new antecedent for peak pattern. Create a new antecedent in your fuzzy logic system that represents the deviation from the normal peak pattern. This antecedent can have a numerical value based on how much the detected peak pattern deviates from the normal, 2 positive, 2 negative. Adjust existing rules. Modify your existing fuzzy rules to incorporate this new antecedent. For example, you can create a rule that states if the peak pattern deviates significantly from the normal, then the likelihood of abnormality is high. Fine-tune membership functions. Adjust the membership functions for the new antecedent to accurately reflect the degree of deviation from a normal ECG pattern. Likely abnormal. If the peak pattern deviation is high, or if there are significant anomalies in frequency or amplitude, then abnormality is likely. Possibly abnormal. If there are moderate deviations in peak pattern, frequency, or amplitude, then abnormality is possible. Unlikely abnormal. If all parameters are close to normal, then abnormality is unlikely. Implement and test. After updating the rules and membership functions, implement these changes in your system and test with various ECG data to see how effectively it identifies abnormalities. By making these adjustments, your fuzzy logic system should be better equipped to identify abnormal ECG waveforms, especially those that deviate from the typical peak pattern. Remember, the effectiveness of this approach largely depends on the accuracy of your peak detection and the precision of your fuzzy membership functions and rules.
Okay, so it's like giving me prompts for GitHub Copilot to change the code or something, or at least that's how we could use it. Current problem, yeah, we need to change process data to look at both positive and negative peaks instead of just the overall number of peaks. So let's do that. It forgot to change those globals. Maybe they don't need to change. So this will be the same. Then we have the amplitude, frequency should be the same. Mean peaks, right? So this bit it changes. And yes, this normalized values will have to change as well, specifically for the peaks. Normalize. It's this line there. Right, it's not being currently used. and the whole return will change. Just do that. So now we don't have any errors that the linter is showing. That's great. Can actually forget to run the application just to show you how it looks like. Yeah, so again, you have those ECG waveforms, individual PQ, RST complexes scrolling through the window, and some of them are normal, some abnormal, and you need to click on the abnormal ones. If I click on normal one, I get a false alarm. If I do not click on abnormal one, I get a miss. This is normal. I click on it, so I get the a false alarm. Then correct rejection. Yeah, this one I do not click on, get a now correct rejection. Another normal. And now a correct rejection. This is abnormal, it's missing one of the peaks, and so on and so forth. Abnormal as well. And once you get to 50 points, it starts going faster, which, by the way, the bot should absolutely not care about. So this is definitely where human will fail, or start failing as soon as the waveforms are scrolling too fast on the screen. There's a video of me reaching 1,000 points. That's the maximum I can do. Go check it out, see if you can do any better. It's on the website. Now, this is what we're adding in the current change. We have this analysis of a fuzzy logic. Potentially later we'll add another column for neural network analysis.
To adjust the fuzzy logic detector in your system to give a higher probability of detecting abnormal ECGs, you should focus on tweaking the fuzzy rules based on the ECG features you're analyzing, namely, frequency, amplitude, and peaks. Since we've identified the standard peak pattern in a normal ECG, two positive To adjust the fuzzy logic detector in your system to give a higher probability of detecting abnormal ECGs, you should focus on tweaking the fuzzy rules based on the ECG features you're analyzing, namely, frequency, amplitude, and peaks. Since we've identified the standard peak pattern in a normal ECG, 2 positive and 2 negative peaks, you can use this information to refine your rules. Here's a suggested approach. Define new antecedent for peak pattern. Create a new antecedent in your fuzzy logic system that represents the deviation from the normal peak pattern. This antecedent can have a numerical value based on how much the detected peak pattern deviates from the normal, 2 positive, 2 negative. Adjust existing rules. Modify your existing fuzzy rules to incorporate this new antecedent. For example, you can create a rule that states if the peak pattern deviates significantly from the normal, then the likelihood of abnormality is high. Fine-tune membership functions. Adjust the membership functions for the new antecedent to accurately reflect the degree of deviation from a normal ECG pattern. Update fuzzy rules for abnormality. Likely abnormal. If the peak pattern deviation is high, or if there are significant anomalies in frequency or amplitude, then abnormality is likely. Possibly abnormal. If there are moderate deviations in peak pattern, frequency, or amplitude, then abnormality is possible. Unlikely abnormal. If all parameters are close to normal, then abnormality is unlikely. Implement and test. After updating the rules and membership functions, implement these changes in your system and test with various ECG data to see how effectively it identifies abnormalities. By making these adjustments, your fuzzy logic system should be better equipped to identify abnormal ECG waveforms, especially those that deviate from the typical peak pattern. Remember, the effectiveness of this approach largely depends on the accuracy of your peak detection and the precision of your fuzzy membership functions and rules.
Okay, I just realized, are you sure about the 2 positive and 2 negative peaks in P, Q, R, S, T complex? Yep.
I apologize for the confusion earlier. Let me clarify the typical peaks in a standard PQRST complex of an ECG waveform. P wave, 1 positive peak, atrial depolarization. Q wave, a small negative deflection, not always present. R wave, a large positive peak. S wave, a negative deflection following the R wave. T wave, 1 positive peak, ventricular repolarization. So, in a typical normal ECG waveform for 1 cardiac cycle, a single PQRST complex, you should expect positive peaks, generally, 2 positive peaks, P wave and T wave. The R wave in the QRS complex is also positive but is part of the same complex. Negative peaks, 1 or 2, depending on whether the Q wave is present and visible. The S wave is typically negative. The exact appearance can vary depending on individual heart conditions and the lead configuration of the ECG. However, this is a general guideline for a normal ECG waveform.
Okay, so shouldn't there be 5 of them? So if we have a normal ECG coming through, that's not normal. That's actually a difficult one to detect. Yet this one. This is a normal ECG and it has 1, 2, 3, 4 P. Right, Q. This one doesn't have the Q. R, S, T. The R is normally negative as well. So there should be 2 negatives and 3 positives. That would be like a textbook. This is not a textbook. PQRST complex. This image, for example, is missing the negative Q deflection. So ideally, there should be 3 positives and 2 negatives. How do we adjust the fuzzy membership functions for this to work? Yep. But it's thinking for long like this is not a good sign. Okay, we still have peaks. Oops, instead of splitting them up, just
Correct. A typical ECG P-QRS-T complex consists of a P-wave, QRS complex, and T-wave. The QRS complex itself typically has a Q wave, negative, an R wave, positive, and an S wave, negative. The P wave and T wave are usually positive. In the image you've shown, the Q wave is not visible, which can sometimes occur in normal ECGs depending on lead placement and individual variation. However, for the sake of setting up fuzzy logic for detecting abnormalities, we can assume a standard ECG should have 3 positive peaks, P wave, R wave, and T wave. 2 negative peaks, Q wave and S wave. To adjust the fuzzy logic to account for the possibility of missing Q waves or other abnormalities, you can set up your membership functions and rules as follows. Membership functions for peaks. You can define membership functions for the count of positive and negative peaks. For example, positive peaks, T. Positive peaks, too few, could be 0 or 1, normal, could be 2 or 3, too many, could be 4 or more. If the count of positive peaks is too few, or too many, then abnormality is likely. If the count of negative peaks is too few, or too many, then abnormality is likely. If the count of positive peaks is normal, but the count of negative peaks is too few, then abnormality is possible, accounting for the missing Q wave. If both positive and negative peaks are normal, then abnormality is unlikely. Here's an example of how you might define one of these rules in a fuzzy logic system. Ensure that your membership functions are well calibrated to the data you're analyzing, and the rules reflect the medical knowledge of ECG interpretation. Also, consider individual variability in the context of the measurement when setting up these definitions. Testing with a diverse set of ECG data will be critical to fine-tuning the system's accuracy.
Right, we'll do this in a second to still solve this problem, technical issue. So analyze waveform function in a game logic JavaScript. Yeah, we sent a post request, that's correct. There's 61 peaks. How about whole words? There's still 25. Okay. Okay, can we split it into the negative and positive peaks separately? And can you actually generate the relevant code? I trust you. Yep. Well, not really, but maybe this prompt will help.
Certainly. To adjust the fuzzy logic detector to consider positive and negative peaks separately, you need to define membership functions for the count of positive and negative peaks separately. Create rules that consider these counts to assess the likelihood of abnormality. Here's how you can define the fuzzy sets and rules.
Right, so breaking the overall number of peaks to positive and negative. Let's close chat Copilot for a sec. Can comment this out. Comment that out. Give me the numbers. And what's abnormality again? Let's do abnormality quickly. Membership functions for abnormality. This is same as before.
This code assumes a standard ECG with 3 positive peaks, including the R wave, and 1 or 2 negative peaks, Q and S waves. The membership functions and rules should be adjusted based on the actual ECG data you're analyzing. Make sure to test and refine these based on real-world data for the best results.
Yeah, we have synthetic, but it's okay. We are using synthetic ECG for now. Testing with real ECG data will be another Flask application, another tool. What else? We're still implementing this. Let's go over it again. We have positive peaks, negative peaks. We got rid of the overall number of peaks. Now we actually need to use those negative and positive peaks to few too many normal. Sounds good. I'll check the actual numbers in a sec. Then we have the abnormality. A likelihood, so unlikely, possible, likely. Those numbers remain the same. yeah, they might need adjustment later. Now we have these rules. Yeah, we need to get our rules correctly. So we have rules based on positive and negative peaks, too many, too few. We don't need this one anymore. This should be rule 5. It's looking at the frequency amplitude. And more rules as needed. Can suggesting rule 7. Okay, let's take it. Would suggest more if I just, yeah, it does medium. It's not a great rule, but it will keep going. No. Okay, so we have those so far. There's some problem with the code. Right, we have abnormality control. Create control system with these rules. Just go remove this one for a sec and just have that comment as a prompt. Right, it's doing rule 1 to 7. It's calling a different variable. It should be fine. And then control system simulation, abnormality analysis. Don't know why is it calling it the same name, but it looks legit. And we have all the 1 to 7 rules, 1 to 4 being rules related to the number of positive and negative peaks, and rules 5, 6, 7 are related to frequency and amplitude. Obviously this is and or. Then we have place. Don't have this bit, do we? Multi-analysis. Compute. Input process data into the control system. It's about that. Computers there. Okay, let's print this. Yeah, I'm not sure about that line. Let's check it out for a sec. Pop it in here. This thing is actually called abnormality analysis. To use the system, you will input the number of positive and negative peaks detected in your ECG signal. Here's how to simulate with example inputs. Okay, so we don't, oops, don't need it for now. We have peaks membership. That's still a problem. Check Copilot for a sec. Peaks is not defined. Fixes should define peaks. Do we need it? We did split peaks into two separate variables, the number of positive peaks and the number of negative peaks. So we don't need the peaks variable anymore in theory. Do we have multiple returns? What do you mean if your process data function previously returned a dictionary like this? Why don't you check what was it exactly? Can you check the code? I'm already doing this. Yeah, I think that's the problem with GitHub Copilot doesn't understand the context very well. Yeah, at some stage we'll need to pop it into GPT-4 anyway. So we might as well do it now. Here is an updated SciPy script. Can you detect any problems with it? The whole code. Remove that last prompt.
The provided app.py script appears to be set up for processing ECG waveform data and analyzing it using fuzzy logic. Here are some observations and potential areas that may need attention. Frequency analysis. The dominant underscore frequency is being calculated as the index of the maximum value from the FFT result. This might not represent the actual frequency. You should calculate the frequency values and then find the dominant one. Peak detection. Positive and negative peaks are detected correctly. Ensure the detected peaks correspond to the ECG components, P, Q, R, S, T waves. Global min, max variables. You're maintaining global min, max for normalization purposes. Ensure they're updated correctly across requests, as Flask's threaded nature might cause unexpected behavior. Normalization function. The normalization function looks correct, but you must ensure that max underscore val is not equal to min underscore val to prevent division by 0. Fuzzy logic rules. You have defined rules for both positive and negative peak counts, which is good. However, you have a placeholder for peaks in the input, which should be updated to use positive underscore peaks and negative underscore peaks accordingly. The rules are combining the fuzzy sets with or, for, likely, and, for, possible, and, unlikely. Ensure these logical operators align with your system's design intentions. Ensure you are using the correct method to extract the fuzzy membership values. The current method using fuzz, interp underscore membership is appropriate for getting the membership grade for a single value. Before sending the JSON response, you are converting the NumPy types to native Python types, which is necessary to avoid serialization issues. Proper error handling is implemented, which is good for debugging and catching unexpected issues. Here's a suggested change for the frequency calculation part. Ensure that you test the application thoroughly after making changes to verify the correct functionality. Also, it would be wise to handle cases where the FFT might return 0 or near 0 frequencies to ensure the frequency value makes sense in the context of an ECG.
Do we have this function? Or wait, let's fix the peaks a bit first. The fuzzy logic analysis function is correctly expecting a single peaks input, but the process test function returning separate counts of positive and negative. That's correct. To modify, accept both positive and P. So normality analysis. Yeah, we have frequency, amplitude, peaks. then normalize once. Then you should update the peaks membership dictionary. Peaks membership dictionary. Positive peaks membership and negative peaks membership. May have 2 returns. First one is okay, the second one isn't. We have results, frequency, amplitude. Right. That looks legit. The app is not running. We need to run it. Still have peaks somewhere. Oops. Still have the same error. Error messaging KZK peaks is not found dictionary. Peaks key is not present in the dictionary. Process. I use instead of peaks. Should update analyze waveform. This one here. Waveform data process data. Converting numpy to integer. Adds this to bits. Why is all the same? Okay, now it's working, but not displaying anything. Why? Likely it does not exist for consequent abnormality available. Right, should be a simple fix. It's a case sensitive thingy. Do with rule 5, 6, 7. Just pop it in, save. Clear. Control F5. Seem to work okay. Seem to work. If I game logic, so what I don't understand. So what if we do workspace? Based on the recent changes in this code, how do we change the JavaScript? Yeah, play silly. Yes, we did split the peaks. We're fetching that sometimes. Analyze waveform. Endpoint in your JavaScript code, you will need to update the code. Let's just edit the console log. Did just add console logging, did it? Because that would not really help. Okay, we have this industrial loan mower working outside, so it will be my cue to finish up. We'll continue probably next week. See how we go, making slow progress. Just make a quick overview. Next week we will fix these values, which is the output of the fuzzy logic analysis. We do have the values working okay, but they're just not being displayed properly on the front panel. Abnormality 0.8. Let's see if it's actually correct or not. So this is abnormal. Yeah, abnormal EEG. Once it's passes, it's abnormality 0.8. This one normal ECG, and it says abnormality 0.5. This one here 0.8 again. This one will be harder to detect. Yeah, it's always showing 0.8 for abnormal. think. Subnormal again. Well, and this is a normal ECG and showing abnormality rate. That was wrong. Seemed to be delayed by 1. Doing that was abnormal, 0.8. And then normal should go to 0.5. Yes, abnormal 0.8, normal 0.5. So it works. more or less. This is normal again, we'll go to 0.5. So that's the probability or not. To check that. Okay, something is wrong. So that's normal. It's just stuck. And this is how the decision is actually being made. So for 4.8, you have positive. Oh, it's still normalizing the number of positive peaks. This is no good, no good, no good. We'll fix this next time. Should be fairly straightforward fix. Just check if by any chance there are any questions. Doesn't seem like. Let me. The stream will be available both on LinkedIn, YouTube. Not sure how Twitch works. The streams just go away after you finish streaming, but all the videos are on YouTube. You can go check them out. The website is available for you to play with. The current ECG games just over there. You can access it from the front page of the website bionicchaos.com, and you can play with it manually, and hopefully this tool, which is a robot playing this ECG game, will be available for you to try out sometime soon. So you know what to do. Like, subscribe. I'm most scared about actual meaningful comments. So if you have any suggestions, requests, screaming at me for doing something wrong, please do let me know. I'll see you next time. Bye.